I use L'Hopital's rule?
No. It's not 0 over 0 or infinity over infinity.
Right. It's not 0 over 0, nor infinity over infinity, nor negative infinity over infinity, which you think about it, it still reduces to infinity over infinity. But whatever. Is that indeterminate? It is indeterminate, but we can't use L'Hopital's rule. So what the heck are we going to do with this?
Change it algebraically.
We're going to do what?
Change it algebraically into those indeterminate forms.
Yeah, can we get it there? Can we get it into one of those forms? This is where L'Hopital's rule is just, I'm not sure it's exactly fun. But it's not that bad because the book makes it sound like it's horrible. Page 305, there's a theorem. It says, if the limit as x approaches c of the natural log of a function equals L, then the limit as x approaches c of f of x equals e to the L. And then it goes on to do all those other stuff. But notice what it is equating. This is just really what we need to say is, oh, well, if nothing else works, maybe we should take the natural log of both sides and see what happens. That's really what Theorem 305 says. So let's do that. So why did I do that? Well, because now I need a function before I can do stuff to both sides of, well, I need an equation before I can do something to both sides. So I had to say, well, this is a function. I'm just saying, let's say it's a function by saying y equals this. I could just as easily have said f of x equals that, but then I'm dealing with f of x, and I don't like dealing with f of x. But if that makes more sense of you to just say, oh yeah, this is a function, I'll just name it f of x equals this. But it's so much easier to write it this way. Because then when you take the natural log of both sides, it just cleans up a lot more nicely. Now you'll notice one little thing here. Do you notice that natural log goes inside limit? So it's saying if I take the natural log of both sides, I put the natural log in here. Do you have an issue with that? I kind of have an issue with it. Well, because it should be on the outside of here, right?
You can't take a natural log of a really.
Right, doesn't matter. It's fine. It's cool. It's just one of those, yeah, it's just one of those things that works just fine, so don't worry about it too much. Now you can tell my horrible handwriting and what an issue it is. Don't want to mix up limit and natural log or things go really wacky. Okay. What are we going to do with this now? Say what?
Manipulate.
Manipulated. No wonder I'm having problems here. I made a typo. Gee. And then I promulgated it. So now that we have the natural log sitting over there, what can we do with that exponent according to the rules of logarithms? Yeah, you can pull it down as a multiplier. Okay, now you're not gonna like what I do. Well, will you agree with me that that's okay to do that? I'm just multiplying it by 1, right? Okay, why did I choose that 1? Well, because I know as x goes to infinity, 1 over infinity is
0.
0. Do I really want 0? Why did I choose that?
Get rid of the
Oh, this is weird. I did something wrong here. Way wrong. So this is going to be the natural log of 1 plus 1 over x over 1 over x, right? Because these guys will reduce out. And so now if I plug infinity in, what do I got? What's the value of the natural log of 1? Ha! I got it indeterminate. Now that it's in the indeterminate form of infinity over infinity or 0 over 0, now I can take it where I need to take it. All that work was just to get it in that form. Whew. And my notes are wrong, by the way. Okay, so now that it's in the right form, to say we're in that 0 over 0 or infinity over infinity, now we can go back and we can say the natural log of y equals the limit as x approaches infinity of natural log of 1 plus 1 over x over 1 over x. And now we can take the derivative of the top and the bottom. What's the derivative of that?
1 over x. Or 1 over 1 plus 1 over x.
Times. Let's take the derivative of this chain rule.
negative x.
The negative x squared. The negative.
And what's the derivative of that?
Negative x without negative.
Cool. So now I've got the natural log of y equals the limit as x approaches infinity of 1 over 1 plus 1 over x.
Equals 1.
Now what do I do? Now I can look at that proof, or I can just say, wait a minute, I know the
E to the power of
definition
1.
here E to the 1 equals y. I know the definition of that. Or I can look at this thing that says, if the limit of the natural log equals a limit, then the limit of the function itself equals e to that number, e to the 1. So what do you want to do? Do you want to remember that rule, or do you want to use the definition of e and natural log?
Already have the definition, so might as well use it.
Yeah, it's kind of like, yeah, sure, I'll remember that, or I'll just remember, once I get to here, I'll just use the definition. Personally, I would say I will just use the definition because I can remember that better than having to remember a specific theorem. I'm not really good at remembering specific theorems. Somebody moves your table too close. So when I plug straight into that, what do I get?
One.
Right? As x approaches 0, x will be 0. As x approaches 0 from the positive side, like it matters, 2x will also be 0. So I've got 0 to the 0 power. Can I use the L'Hopital's rule? Nope. No, I can't. Well, when all else fails, let's use that rule again and say, well, my function's name is x to the 2x. And then, of course, I'm switching to y because it's easier for me to deal with. Whoops. I lost my limit. Nobody even said anything. Still need that limit for me there. Now I'll just take the natural log of both sides. So the natural log of y equals the natural, the limit as x approaches 0 from the positive side of the natural log of x to the 2x. Now why did I decide to do that? Well, there aren't many other options. I know that to use L'Hopital's rule, I have to have 0 over 0 or infinity over infinity. How can I mess with that according to this section in the book? You take the natural log of both sides. That's how you can mess with it according to this section of the book. Well, let's make this into a multiplier now. Got natural log of y equals the limit as x approaches 0 from the positive side of 2x times the natural log of x. Now we'll use the same trick we used before. Multiply this by 1. We can get to 0 over 0 or infinity over infinity. Do we really care which one we get to? No, we don't. Natural log of y equals the limit as x approaches 0 from the positive side of 2 natural log of x over 1 over x. And now what happens when we plug 0